Yeah, I can see.
Okay, so we'll get started. What we will go over today is the first part of two um, topics. The first topic that's covered is semi-supervised learning, and we'll kind of understand first what's the difference between semi-supervised, as they refer to it in the class, and self-supervised learning, and the various techniques that over time have made self-supervised learning what it is today, and maybe it's even advanced more since class ended because there's an active area of research. So, in order to understand semi-supervised learning, first, if we look at what is supervised learning, it's basically a joint distribution of samples X and labels Y. So X and Y are chosen from a probability distribution of X is the samples or images, for example, and Y are the labels, and within which we maximize the expectation of X and Y chosen from the probability distribution XY and the log of probability of Y given X. So that's the classifier that we train. So essentially what we do is sample a pair of X and Y, assuming that, the X's are all IID, meaning independent and identically distributed. We don't know the underlying distribution, but we keep sampling the points and optimize this equation in order to find the best classification or classifier. Um, in case of semi-supervised learning, at least the framework under which semi-supervised learning operates is, let's say, there is an unlabeled data set, and the assumption that is made is the unlabeled data is coming from the marginal distribution of the same joint distribution P of xy. This is kind of an important assumption, although it's a mathematical assumption, and in practice it doesn't often hold. But there are consequences to that we'll see when the distribution of unlabeled data is different from the joint distribution of the supervised data and what consequences it has. But the fundamental assumption that's made in semi-supervised learning is the distribution X, the marginal distribution of X, comes from the same distribution as the joint distribution of what is typically used in supervised learning. So we have a bunch of unlabeled data having the same distribution as the distribution for the supervised training, which has the data or the images. To keep it simple, let's assume that it's images we're talking about and labels. Then this DS is the case of supervised data, images, labels, Y, that's the distribution. And we assume that there's a lot of unlabeled data where there are no labels, but the samples or images are still available. So the goal is still same as before, meaning that the supervised learning of the labeled data set, but with access to a lot of unlabeled data, which then hopefully we can use or put the unlabeled data to good use in order to improve the performance of the classifier. That's kind of the goal of semi-supervised learning, right? And as I repeated a couple of times already, the assumption is that the unlabeled data corresponds to the same joint distribution that the supervised data came from. Although in practice, this is not often the case. So what we will do in the next hour or two is kind of learn about the various different techniques that are used in order to achieve this goal. So fully supervised classification, there is the training data, there's an image and the label, and our goal is to be able to predict the label for the new images. But it's semi-supervised. The assumption is, what if we have a small number of samples and then labeled samples and a lot of unlabeled samples? Can we somehow use the unlabeled samples in order to improve our performance or get good performance in the low data regime for our classifier. And why do we do this? We do this because, as we've discussed many times before, labeling is very time consuming, and often label data is hard to obtain in certain domains like medicine and a few other domains, even in drug manufacturing, things like that, drug discovery and so on. So the hope, if you will, of semi-supervised learning as compared to self-supervised learning. In self-supervised learning, there are no labels whatsoever. In semi-supervised learning, the distinction is that there's some data with labels that's available, but our hope is to be able to learn from a lot more availability of unlabeled data. So that's kind of the goal. Use the unlabeled data that we have to make supervised learning better. That's why it's semi-supervised as opposed to self-supervised. Self-supervised implies, at least for the purposes of the class, they make this distinction that self-supervised means there's kind of no label data. You have to pick up the labels, and we spend a lot of time learning all the different techniques, contrastive estimation, MOCO, and so on and so forth, right? Whereas we'll see a different set of techniques, somewhat similar, but different at the same time, or techniques to learn from, or techniques that are applicable in the semi-supervised learning context. So again, this is just an illustration of the view of semi-supervised learning, which is to say that data that has labels is like gold because it's highly valued, but much more than gold, which has to be dug up from the earth. There are lots and lots of rocks that are freely available, and that's the equivalent of unlabeled data. The question is, the eternal question that many people have been after, which is, can we turn rock into gold? But in the context of data and supervision and semi-supervised data. So that's kind of the concept or basic attempt at what we are trying to achieve with semi-supervised learning. One of the interesting things that is kind of originally the goal or the belief of many ML practitioners was semi-supervised learning would help immensely in the low data regime. That is when our label data is a lot less. Obviously, this is the domain, let's say, of high data regime, if you were to call it that. That means we have a lot of data that has labels. And here we have very relatively few data that has labels. So the original or the belief, I would say, of many ML practitioners is we would gain a lot by coming up with techniques of semi-supervised learning, especially in the low data regime. That is to say, in the regime where we don't have many labels, we would be able to improve the performance of the classifier. But whether there is any benefit in the high data regime, most people thought, well, maybe not. Supervised will probably beat semi-supervised. If we have a lot of data with a lot of labels, you're probably better off using supervised learning. But the dream, or kind of if we get to this state, it's really a significant achievement, and the state that will give us, immense joy or really something to shoot after is not only do we get with the use of semi-supervised learning better performance in the low data regime, that is, we get a lot better performance from the classifier in the cases where we have low data, that means low labeled data. But the contrast between the left graph and the right graph is you can see that the red line is above here. So this line is above the blue line. So the thinking or the magic, if we can make this to happen, it would be awesome, is not only is our performance of semi-supervised technique, not only is our performance of the classifier using semi-supervised technique is better in the low data regime, but somehow it also contributes to making the performance of the classifier better in the high data regime. So think of this as kind of the reach goal for many SSL researchers. And what we will see towards the end of the lecture is that this, with today's techniques, has been achieved. That is to say, semi-supervised learning techniques that are currently available help us not only to get better classifier performance at low data regimes, but it also helps us get significantly better performance on than supervised labeled data available, even with a lot of the data that is available with labels. The semi-supervised techniques help the classifier perform better, which we'll see towards the end of the lecture. The core concepts I
have a quick question.
Yeah, go ahead, Martin.
Yes. So you mentioned in the end that that some part of it is achieved, but do you, like, maybe you can just to what is the actual state of the art kind of result right now on these two curves? Like, does it make sense for a practitioner to make a semi-supervised system or not? Is it worth it at all right now in the current state?
Yes, I don't. Towards the end of the lecture, we actually get numbers for the performance of semi-supervised learning compared to supervised learning. Of course, as with anything else in any domain, it's benchmarked with reference to particular data. So, as they say, your mileage may vary, right? Because typically they have done it, at least the two data sets that I see repeatedly referred to in this kind of research is CFAR10 and SVHN. So, will that translate? Of course, it's better than MNIST, but will that translate to, and I think they do, I think compare ImageNet data as well. So it does translate to larger data sets. But again, keep in mind that this is in the specific domain with a specific set of data. I have not seen, although it's possible that it exists. I haven't had the time to research. For example, is this true in the medical domain, which is something they refer to as it would be really useful if it, because in medicine we don't have labels. Now, does that mean that they've applied these techniques to the medical domain and have achieved the chart that I'm showing you in the right? At least this lecture doesn't point to it, but at the same time, I have recently seen some papers, not in this context, but the Stanford Human AI team usually has guest lectures for an hour and stuff, and I recently attended one where they have used semi-supervised technique with, I forget it is MRI or CAT scan or whatever, and I've shown similar to this result.
Okay. Yeah, because I mean, some of the results, it's more towards the left one, and then on some, but then only they look at small parts of the curve, like not a nice curve has been drawn for everything. I think that's what I feel like for the results that they show.
So yeah, obviously this is more.
Comment on it on my side.
Sure, sure.
So about the practical side. First, like in Kaggle, a lot of winning approaches using some kind of semi-supervised stuff like pseudo labels and its derivatives, and also relabeling noisy data from practical side can also be very useful. When you are not sure that all your labels are correct, and it is in a way similar to what we will discuss today. Also, as a noisy student paper, I believe it was about 2% increase in ImageNet state of the art on ImageNet, and that was like substantial at that moment. And also until lately, the meta pseudo labels paper results was also the state of the art on ImageNet. I see that now it's something else, but still that is also very practical even in this high data regime. On the other hand, you might, as we will see, many of these approaches rely on data augmentations, and therefore, in a very similar to this unsupervised training, like a lot of benefit we get from it relies on the quality of the augmentations, and I believe we will be at least a bit covering this in this lecture. So, yeah.
Okay,
Yeah,
that makes a lot of sense. Thank you. Yeah. Yep. Sorry. Go ahead, please.
yeah, and to your point, Morten, the curves that are obtained are discrete. This is more of a concept curve, so they can kind of make it continuous. But as you say, the comparison that's often made is, obviously pick a point in the low data regime, because again, a lot of it, partly because of what Otto said, you have to do a lot of data augmentation, as we'll see, and a lot of different types of data augmentation in order to get the benefit from semi-supervised learning. And so therefore, they do it at some fixed ratio of what, let's say, and we'll see all this as we get into the rest of the lecture. If suppose 50,000 labels are available, you use something like 500 labels and you get a data point in the low data regime, and then you compare it to the data regime of 50,000 labels, right? So there are 2 points on this curve, but it's not primarily, I think, from a computing standpoint and limitations and stuff, they don't sweep across, although in one of the tables I recall, there are multiple discrete data points, 250, 500,000, 2,000, something like that. And then you can draw a curve like this. But otherwise, it's typically one low data regime point and a high data regime point.
Okay, great. Thank you.
Okay. So the core concepts that we'll use in order to kind of gain understanding of what is done in semi-supervised learning are listed in one slide, but obviously each of these will be covered in some depth. Unlike in the previous lectures, the thing I will say is this lecture is more of a pointer to the papers. They do not, except for certain specific techniques that we will get into in some detail. Even in those cases, they can just present or they can just point to the paper, kind of discuss the concepts, not a great detail about the math. In some cases, I don't even understand the math, and I'll then need to go ahead. If somebody else has more of an intuition, feel free to explain that, jump in and add to the lack of explanation that I'll be giving with respect to the math. But the core concepts are not that difficult to at least get an intuitive grasp on. So the concepts are confidence versus entropy. So the confidence has to do with the confidence of our classifier, and then the entropy will be the entropy of the classifier or as applied to the unlabeled data. So we have this whole, there's one paper referring to entropy minimization, which talks about the math behind take the classifier which you have trained on labeled data and apply it to the unlabeled data, and make sure that the result is that you get low entropy output on the unlabeled data from the classifier. That is, by doing that, what you're saying is make the classifier confident not just in the label domain, but also with the unlabeled data. And this ends up regularizing the classifier, which helps improve the performance of the classifier. So that's one technique, and there's a paper referring to the math behind it. We'll see that. Then pseudo labeling is one where conceptually what you do is you train the classifier on the label data, and then use the classifier that you've trained on the label data to make predictions up on the unlabeled data, and add those labels which the classifier has predicted on the unlabeled data as data points. So it is as if you do self-training. That is, you train a classifier on label data, use the same classifier on unlabeled data to predict labels, and then use those labels as proxy labels to again retrain the classifiers as if you have generated new labeled data point. So it's training the model on its own outputs. Of course, you have to be tricky and careful because this is like self-confirmation bias in human decision making. If you believe something, you'll tend to believe it even more. So we have to be careful about when this kind of technique can go wrong. But that is one of the approaches or one of the techniques. Then there is this whole concept of virtual adversarial training. So the idea here is that in case of GANs and stuff, we have seen how the models can slowly change from one label, like from producing one label output to another label output. So somehow in this high dimensional vector space, there is a direction in which if the model is pushed or is moved in some direction, then it's likely to change its output from one label to another label. And in the virtual adversarial training, what we try to do is identify those directions and make the model robust to those changes. By that is meant if the input data is the same, but I push you in that direction where you're likely to change the label, make sure you don't change the label, because you know that both the inputs you're getting are the same, even though they have been augmented in different ways. And by doing that, you enforce some constraints on the classifier, which makes the classifier learn things about the labels that enable you to do a much better job of classification. So that's kind of virtual adversarial training, and we'll kind of get into, as I said, a little more detail in each of these, right? And I kind of mentioned one of the techniques already when I described the virtual adversarial training, and that is of label consistency. So as Arto already mentioned, we will see much like we saw in self-supervised learning. Remember the dog image and how we rotate, crop, do a bunch of augmentations to the picture of the dog. It's the same thing. We do a significant number of augmentations of the samples, which all have the same class. So that's simply done by taking an image such as the image of the dog and then modifying it, meaning augmenting it. And the augmented image and the original image we know belong to the same class. And by ensuring that the label that our model produces, because these are just two augmentations of the same class, is in fact the same, by making sure that the label remains consistent through the augmentation, we make the model learn or things about the image that then helps us in the classification task. So that there are multiple techniques that make use of this approach of consistency of labels through augmentations, or that means the fact, and I think Arto alluded to it in one of our earlier lectures, if you consider human and we anthropomorphize the problem, then we can say we tend to view objects in our natural life in all kinds of different orientations, for example. So we are, so we grow up, or we kind of have this inbuilt capability to know that a hammer is a hammer regardless of the orientation in which it appears to us in life. And you can think of label consistency as somehow teaching the networks that the same thing is true. That is, regardless of the augmentations of how you see a dog is a dog. And there are various techniques, and we'll talk about 3 different ones: pi model, temporal ensembling, and mean teachers. The other thing that we'll touch upon towards the end, these are all kind of, I would say, historical techniques and concepts that were applied. But even though up to this point, we were I think, not in the realm of where performance was better than the supervised, at least in the high data regime. Then there are regularization techniques. A lot of these techniques end up regularizing the classifier, which means basically they make the performance of the generalization capabilities of the classifier much better than before. And these are well-known regularization techniques, right? Weight decay, dropout, data augmentation. This particular one is for those of you, I think many of you are already familiar, but mix-up is where we mix 2 different images, for example, and mix their labels as well, and have our classifier predict the mixed up images and the mixed up output. A cutout is, taking out a portion of the image and a variation. So these are also data augmentation technique, and we'll see, for example, that mix match is kind of a takeoff of mix up, but applied in a semi-supervised manner. And then there is this whole technique called unsupervised data augmentation. And finally, something Arto already referred to it when he was commenting, the noisy student paper, which kind of takes on a bunch of these kind of techniques and applies it, and has gotten much better performance, especially, he mentioned about 2% better on ImageNet than the supervised. So this is just a quick flyby of the various things that we'll be discussing in the rest of the lecture. Okay. The first one is entropy minimization. Here is the reference to the paper. And as I said, the idea is train the classifier on label data. And if we have a lot of unlabeled data, then make sure that the unlabeled data influences the classifier in some way. That's what our goal is, right? We have a lot of data. Think of it as the stones picture, and we want to make the classifier better. So what do? We take the classifier, ask it to predict on the unlabeled data, and kind of ensure that the predictions are pretty confident on the unlabeled data as well. And by doing that, that is by minimizing the entropy of the classifier on the unlabeled prediction. That is the same as saying that the classifier probabilities of its outputs on unlabeled data is small. And this ensures that the classifier is learning something about the data. That is, it's learning the underlying structure of the unlabeled data by trying to be confident and therefore having low entropy on its predictions on that data. And by doing this, we improve the performance of the classifier on the label data or on data that it will see in the future as well, right? So that's very simple way to do semi-supervised learning. And this paper talks about it. Again, these are, I believe, original ideas, meaning things have moved much farther beyond where these things are today, but these are kind of foundational concepts in the semi-supervised learning technique. Then we kind of move to the pseudo labeling concept that I talked about. It's somewhat similar. Ask the classifier that's already been trained with label data, and you use it to predict the labels on unlabeled data. And you don't pick all of the predictions. You just take the predictions, the most confident predictions that the classifier produces on the unlabeled data, and use them as labels as if they were original labels that were provided to you. So this is the case of self-training. That is, you use a network, a trained network, which is trained with some amount of labeled data, use it to predict on unlabeled data, take the predictions which have been predicted with a high level of confidence as if they are the ground truth. So think of it as proxy ground truth, and then thereby increase the amount of labels that you have and retrain the classifier on the whole labeled and proxy label data, and then use that going forward, right? And to a certain extent, if you think about it, these two techniques are somewhat related to each other, because what you're essentially doing in this technique is also kind of minimizing the entropy and using the labels that are produced by the minimum entropy, because minimum entropy on the unlabeled data in turn implies high confidence predictions, right? So the more confident predicting classifier has lower entropy in the output probability distribution of the classes. So in effect, these two techniques, pseudo labeling and minimizing entropy, both on unlabeled data, is kind of analogous or twins of each other. Then we get into the confidence versus, so this is just an explanation of the confidence versus the entropy. So if you assume, for example, that there's an image, and then there are three classes in the image, y1, y2, y3. Here's the probability distribution for, let's say, classifier A. Classifier B has these probability distribution. Obviously, this is a much sharper distribution from classifier A, whereas classifier B, it gives a lower probability to the correct class and increases the probability of the incorrect label as well. So this one has a lower entropy. So that's what, more confident, and it has lower entropy. So in other words, he's trying to say entropy minimization is kind of similar to training on confident predictions as pseudo labels. So there's just an explanation that pseudo labeling and minimizing entropy are kind of similar to each other. Right? Then we get into the third concept, which is label consistency with data augmentation. And if you've been following along on the class, this is the image we used in a lot of the self-supervised training, and he's deliberately used the same image to convey the meaning that a lot of similarities exist in the approaches we use for self-supervised and semi-supervised techniques, but with a slight twist. So the concept is that of label consistency, right? So to create kind of two different versions of the image, and if you make sure that the logits thing before the softmax, the output before the softmax layer, you can pick whichever close to the output layer for this purpose. If we ensure that the logits that layer is outputting are similar for two images which have been augmented because they are images of the same object, then we can claim that the classifier has been forced to learn something about the label, or something about the data, or something about the structure of the data, right? And if we do this repeatedly for a lot of unlabeled data, then the classifier is getting regularized, which means it gets better at detecting the labels, right? So this is the idea behind label consistency, right? And these are viewed as label consistency constraints on the data, right? Using a lot of data augmentation. And the more data augmentation we use, the better this technique gets. So this is where you get the label consistency between the image on the left and the image on the right, and make sure that the logits output of a layer, let's say the outermost layer before the softmax, are similar, and ensuring this gets us to be able to regularize the classifier a lot. And we use unlabeled data for this purpose, right? And the more the data augmentation, the more the regularization. So you can see that, something like about 10 different techniques of how you can augment it. You can do color distortion, you can drop, you can resize, flip, add noise, blur, all kinds of filtering, and all of these ensuring that the network remains consistent in its prediction of the labels. Obviously, you know that this image and this image should predict the same label, and ensuring that on unlabeled data, there is consistency in the label between this image and this image, or this image and every one of these images, ensures that the network learns something that it can then use in its prediction going forward. So that's the basic concept, right? So you take an image and you do stochastic optimization. Stochastic basically meaning some random optimization. You can pick any one of the others other than the original. And it can even be a sequence of these augmentations, for example. And you find for each forward pass of the labeled data, to kind of regularize the supervised contrastive or supervised cross entropy loss. And for the contrastive, there is something called you do a different kind of loss for the case where you are trying to do the augmentation and ensuring label consistency, right? So that is the label consistency loss between the outputs of the models with the two different and two different views. And you make sure that for labeled data, you use both the losses, and for unlabeled data, you obviously have only one of the losses because you don't have the cross entropy loss since you don't have the label. So you do all this and then you figure out, you apply the technique and you find that the classifier gets better, as we see. So the paper that they refer to in the rest of the early part of this lecture is something, is what they point to here, realistic evaluation of deep semi-supervised learning algorithms. It's a paper which compares various techniques, and apparently, at least from the explanation they gave, it seems to be a very good paper because it does a lot of ablations. It even corrects errors in the past work that has been done in this area, kind of improves the baseline performance of some of the models because they tend to do it in a proper way, and so on and so forth. So this paper seems to be a very good one to go and look at in greater detail, keeping in mind that this is dated by now. So some of the results that it talks about are no longer the case. They've all been superseded and better results have been obtained. What the paper concludes is no longer true. But I think the techniques that they explain and the comparisons they do are all relevant at the time the paper was published. So 3 different techniques that are used in 3 different techniques are explained. One is called the pi model, and these are all variations of the basic idea of label consistency. One is the pi model. The second is called temporal ensembling. The third is mean teacher. The math for at least this third one is somewhat fuzzy to me. And as I said, if somebody else has a better explanation, feel free to jump in. Then again, the same thing for virtual adversarial training. The math behind this is fairly interesting and complicated, but they don't get into the math too much. But if you're so inclined, you'll need to do some reading on your own in order to get a better grasp than I'll be able to give, because I'll just talk very superficially about the math behind these techniques. But we'll discuss each of these: pi model, temporal ensembling, mean teacher, and virtual adversarial training. All of them are variants of the label consistency technique, right? So let's talk about the pi model. So in the pi model, here's what happens. The first thing we do, obviously, is the same thing as what we will do typically with any kind of label data. You have the label Y and you have X, which is the image, and you augment the image. You could think of it as one of the augmentations that I have already shown you. There are about a dozen of them that was shown in the paper. Let's say we pick one of that. It's also stochastic in the sense that you could potentially use not just one augmentation, but you could kind of combine them in sequence, hence stochastic. That is, you could randomly have combinations of algorithms or pick any one of the algorithms. The network itself is also stochastic in the sense that sometimes you have dropout, sometimes not. So there's, stochastic augmentation. Think of it as stochastic network because you're using dropout. And then you do this, you have in cases where you have the xi turned into zi, but you have the label for the label portion of the data. So you do the cross entropy loss for them. That is where you have the labels. But when you don't have the labels, then you do a squared difference between the augmented image, which is this zi tilde guy, and the non-augmented original image. And you kind of do the squared difference. And then combine these two losses by using a weight. And the reason why this weight is interesting is you can think of it as initially when you're bringing up the network, you kind of give it a low weight, let's say, because you to the squared difference, because you're kind of relying more on the label data. But over time, as your network gets better at kind of detecting and ensuring the consistency, then you can increase the weight that you apply to the square difference loss and compared to the cross entropy loss. So this, again, the weight can vary with a schedule, and you weight these two losses and make sure that that is the combined loss you use in this technique. So this is what is referred to as this approach to training the model in a semi-supervised manner. And you can see it is semi-supervised because obviously you use labels for a portion of your training and use label data, which is why the cross entropy exists, whereas you use the square difference for the unlabeled data, and that's the pi model. Any questions? Okay, so here is the algorithm of the pi models, and it's just, you can see xi is the training, yi is the labels, this is the weight, and each of this, you use a neural network with trainable parameters. It's stochastic because you use dropout, you do the augmentation, and for each of the mini batch, you take zi, which is the original image, you do the tilde with different dropout and augmentation, that's the zi tilde, and the loss is the combination of the loss combined, which is your basic cross entropy loss. This guy here is the cross entropy loss. This guy here is the squared loss, and you combine them using some kind of a weight, which if you think about it, it probably use small numbers to begin with, and then you increase the number and then go through and train. And you get the output, and we'll see some of the results later of comparison of this. The next variant, it's just a variant, as I said, of these different models, is the temporal ensembling model. So the temporal ensembling, here is the issue that they try to address. See, in case of the pi model, what you have to do is every single augmentation of every single image, you do forward passes and of the two different views all of the time, right? So you can imagine how many images you'll need to push through this. If for every single image if the unlabeled data, you'll be kind of doing the augmentation and pushing it through this pi model network. So that's a lot of forward passes, right? And it's therefore quite expensive. So what the temporal ensembling does is to say, I am going to keep a moving average of the sample embedding for every single sample in my data set. So if I have a dog, I'll be having embedding of the dog at the output of this, and I'll kind of be storing that. And then anytime a dog on comparison, comes up, a dog augmentation comes up, I'm going to not recalculate through the forward pass, but I just make sure that the consistency is enforced across time between the stored embedding and the new embedding that I get, right? So you still do the stochastic data averaging and the stochastic network, but you kind of only do the embedding for a portion of it, get the embedding every time in the forward pass, and these embeddings should be closer to some historical version of the sample embedding that you already have, which is stored. Now, again, as I said, the details of how that is done, you'd probably have to go through the paper to understand it, but that's the concept. That is, you store an embedding and you make sure that the for the label consistency loss that you're after, that you just make sure that the next augmentation is somehow close to the stored embedding you have for that sample. So you don't push the sample through every time. Now, obviously, you can immediately kind of get the, other than that, it's the same as the pi model, okay? So this then is the pseudocode for the temporal ensembling approach. And again, you can kind of see it's the same thing for each of the mini batch, kind of calculate the ZI, the loss, very similar distance, except in this case, you kind of accumulate the ensemble predictions and construct the target vectors by bias correction. So instead of, the temporal ensembling is a variant of the pi model, which tries to store some embeddings and tries to make sure that the new embeddings aren't all that different from the stored vector, thereby ensuring label consistency, right? But we can, and the idea here is you tend to not have to pass the original and the thing through, thereby trying to improve the, not just the performance, but how much processing you have to do compared to the pi model. Then there is a variation on temporal ensembling. The issue with temporal ensembling is the fact that now you have to store the embedding for every sample of that you have. So in that sense, you're now going to begin to have the issue of not scaling with the size of the data set, because as a data set and you have huge number of unlabeled data, you're not going to be able to maintain all the moving averages of every sample in the data set. This then leads to the next idea of the mean teacher. Now, this is where, again, I did not go through the paper itself. So the math behind it is something that I'll not be able to explain to you, how they amortize the running average and keep an exponential moving average of the embeddings and keep an exponential moving average of the parameters and use that instead of the way that it is done in temporal ensembling. So if anybody else has an idea or can explain more of the math behind this, please feel free to jump in. But the basic concept that I have is that the teacher model, in a sense, which is the model keeps an exponential moving average, and that is then ensured to be label consistent with the new model that, right, or the new data that it comes in. So that is the consistency cost and the typical cross entropy loss. So in other words, keep in mind that the basic concepts of label consistency remains the same. It is how we do it. In case of pi model, we push it through every time. Case of temporal ensembling, we say, oh, I'm going to store an embedding and kind of keep track of my stored embedding, and the new embedding shouldn't be very far from each other. Then the mean teacher approach says, well, that second approach doesn't quite scale. Therefore, let's do the following. Let's kind of have an exponential moving average of the parameters of the model and make sure that the new data doesn't change the parameters too far from what the exponential moving average is. That's at least my understanding of how the mean teacher approach and the temporal ensembling approaches are just variants of the basic pi model approach. But again, the devil is in the details, and how exactly this technique is implemented is something that you'd have to go through the paper to understand. Any questions or comments? Anybody else have a better explanation for this than what I offered?
Well, I agree with your explanation. So that's my understanding of mean teacher as well. And yeah, so I think that's perfectly valid. So the idea is that we don't want these predictions to change too fast. So we keep this exponentially moving average weights and make sure that the predictions are consistent. And yeah, so I guess there is nothing more to it, actually.
Thanks. Okay, then these are three techniques we looked at, right? A phi model, temporal ensembling, mean teacher. All of them imposing label consistency on the unlabeled data, having combination of consistency cost, and which can be some kind of distance metric between the two data points, augmented data points, and the classification cost for the labeled data. Now we get into the other concept, a completely different concept called virtual adversarial training. Now, there are two words we use, virtual and adversarial, and each of them has a specific meaning. Again, this is one where they just have a match slide, but I can't, again, tell you much more about the math than the concept behind it. Again, if any of you are more familiar with the details, feel free to jump in, but I'll give you my best explanation of what I understood virtual adversarial training to be, but in a conceptual manner. So the idea of adversarial training is, if you recall from the GANs discussion we have had and stuff, let's consider that MN is 2 digits, right? Let's say a 5 changes to a 9 somehow. Now, in the high dimensional space that these things are embedded in, let's consider a latent space, for example, and stuff. If we perturb the model in a particular direction in the high dimensional space, it's likely, latent space, let's say, then it's likely to move or shift from a 5 to a 9, right? So this method, as I understand it, what it tries to do is that the classifier is fooled into classifying a 5 as a 9 if it's pushed in that particular direction in the high dimensional space, right? Now, the way what you want to do is prevent the classifier from being fooled, which means what you do is you identify the direction in which, if it is perturbed, it would misclassify, and you ensure you do the opposite, meaning you make sure that the classifier is robust to disturbance or noise in that direction. So, you are trying to say, once I identify the direction in which the training can become adversarial, I make the classifier robust to changes in that direction or the perturbations in that direction. So it's like adding noise in the direction of the perturbation, which is likely to cause misclassification, making the classifier robust to addition of noise. So that's kind of what is done here. The reason why it is called virtual, or at least I would say that's the concept of adversarial training in the GAN domain and so on. Why is it then called virtual adversarial training? Well, in our case, we don't have the label. So we cannot, for example, say, oh, a 5, which is a label in the MNIST example, is being changed to a 9, because we don't have the 5 and the 9 available for the unlabeled data, right? So, and this is where the math details elude me, but I'll again explain conceptually, because that's what they have done in the class as well. If you really need to understand the math, you'll have to kind of go through it and dig into the details. But the idea here is, since we don't have the labels, what apparently is done is you look at the distribution of the classes, and instead of saying a particular class, meaning like a 5 and a 9, which is the labels for the class, you don't identify the perturbation direction for one class. Instead, you take some distribution of classes and some distance metric between your unperturbed data points and the perturbed data points, which means, again, mentally, conceptually think of classes like 5 and 9. If you keep referring, at least to me, if you keep referring to the labeled example, then you can kind of get an intuitive idea of what is going on in the unlabeled case of the virtual adversarial training. So take a distribution of classes and some distance metric between unperturbed data points and the perturbed data points, and try to figure out the direction that maximizes the scale of the difference. And this is where the details of the math are quite intriguing. But apparently, if you can linearize this scale term, which is the KL divergence term, right, then you can solve for the direction which causes the disturbance using power iteration. And if you recall, again, we touched on power iteration in some other context in the supervised training, which is, you go through the repeated iterations and it gets better and better. That's kind of the very rudimentary explanation of power iteration. So once we identify the direction, make sure that you enforce structure on the classifier on the unlabeled data so that the perturbations do not cause a change in the class. And, or stated another way, the classifier is robust to noise in that direction. So conceptually, as I understand it, and again, this is where anybody else jump in and
I can show
add.
an implementation of it if you'd like. I have been working a bit on something similar, and if we have time, I can quickly show code that implements kind of similar thing, and yeah, that actually is not too big to grasp.
Okay, sure. Let me just finish up on this, and then as soon as we maybe we can jump to that and then get back. Let me just finish up on this particular explanation. It doesn't go too far, and then maybe you can get into your stuff and then return back. So that's kind of the virtual adversarial training. It's not a real adversarial training because it doesn't, we use some math concepts which help us to identify the directions in which we need to make the classifier robust. And the directions are determined not by using individual classes, but some combinations of the distribution of the classes, right? So that's the reason why it's called virtual adversarial training. So keep in mind that the adversarial part comes from, making the classifier misclassify things and making the classifier robust to that. And the virtual part comes because we don't have the labels, and therefore we have to look at it from the distribution of class perspective to identify the direction, and then linearize it and use a power iteration to determine the direction. And once we have the direction, then we can do the improvements to the classifier to make it robust by using the label consistency thing. So this is again the code, and I think if Arto has an example, we can go look at it. So let's stop here. Maybe I'll stop sharing, Arto, and you can go through your stuff, and then we'll come back and look at some of the results of this paper has discussed.
Yeah, sure.
Go ahead, it's yours.
Okay. Yeah, here's, I'll try to keep it short. So here is an implementation of this kind of virtual adversarial training. I've used it for text rather than images, but in case of images, it's even more straightforward. So the idea is, let's just walk through this function that computes an adversarial loss. So the inputs would be a model, an embedding in case of text, and in case of image, you can imagine this would be just a raw image. So we, and in case of text, we need to use some continuous inputs here because we want to perturb them, and it's non-obvious how can we perturb discrete inputs that are tokens, for instance, but we can perturb embeddings in case of text, right? And then we have this logits inputs that are you also the outputs of the model that the outputs that on the unperturbed batch. Okay, so what we do, we initialize some noise tensor, and it would be of the same shape as an embedding, so the input to our model. And there is some hyperparameter to choose that is variance of the noise. But otherwise, this is just a normally distributed noise. And the idea is we want to make, so now it's a normal noise, just a Gaussian noise, and we want to, but what we want to do, we want to compute an adversarial perturbation. So now it's just random perturbation, we want to make it adversarial. So we want to change it in a way that it affects the outputs of the model the most, right? So what we're gonna do here, you can see that we enable the gradients for this tensor. So it now requires gradients. And we construct a new input to the model, which is a sum of this noise and the embedding of the original input. And then we compute this adversarially perturbed logits. So now we have two kinds of logits, just a clean logits from the model and this adversarially perturbed version. Then we compute the KL divergence for these two. Essentially, these are two distributions, right? So the distributions of the outputs, like not distributions, but logits from which you can make distribution by applying softmax, right? So essentially, those outputs assign some probabilities to the outputs. So we can compute the KL divergence for these two outputs, and then we need to compute a gradient for this KL divergence with respect to the noise, right? And then we need to change the noise in a way that it is maximizing this gradient. So basically, what we do this gradient ascent for k steps, and in practice, this is done for just one step in the papers I have been referring to, and we also need.
So that's the power iteration part, right?
Yeah,
like you just do it once, but that's kind of the power iteration.
Yeah, and we have here like a constraint optimization problem. So we need to do this projection of a noise to make sure that it's basically a normalization. You can see here is a small function, and we have different choices of how to what kind of norm to compute to basically to select this direction of a gradient. And you can see that in the simplest case, if we want to use L1 norm, it would be just a sign of the gradient in the corresponding directions. Otherwise, it would be otherwise it would be a bit more like but that's just normalization. So what we do here, do this gradient ascent in the adversarial direction, and we do this for some k steps. So we do this iteratively refine our noise to be the adversarial noise, and once we are happy with the results, so we got this adversarial noise, we finally compute this adversarial logit that would be used for our loss function. And in the end, we will just compute some loss, basically the distance matrix. So we need some distance metric between adversarially perturbed logits and the original logits. And the distance metric in this case would be symmetrized KL divergence, which means just a sum of KL divergence in both directions. You can see it here. And because the KL divergence itself is not a proper distance metric, but we can make it so by like symmetrizing it kind of. And in case of if we are doing that's in case we are doing classification, but in case we are doing a regression, we can use MSE, for example, here. So that's basically just some distance metric that we want to use to make sure that we penalize the deviation of adversarially perturbed outputs from the original outputs. And why this can be used for semi-supervised training? As you can see, we do not need any labels to compute this loss, right? We just need an input, and then we can compute. We can just basically what we do. We ensure that the loss landscape is relatively smooth, so we do not have any strong adversarial direction. Yeah, so that's basically it. And in my experiments, I haven't really done experiments in semi-supervised setting, but it is also claimed to improve the results in just supervised classification, but it also improves the adversarial robustness of the model of the classifier. And in my experiments, it both improved the classification accuracy for smaller models. But for example, in models like Roberta, I haven't observed much of the classification accuracy improvement, but the adversarial robustness was better. So it means that it is less confident on the wrong predictions. So the
yeah, I was going to ask Arto, how do you test its robustness on adversarial predictions? What is the means by which you determine that it's gotten better?
Yeah, I'm not sure if I can find the right results right now, but I will try maybe just to show something. I don't know if I have here some relevant outputs. Yeah, essentially there are some adversarial data sets, so that are constructed specific, like handcrafted adversarial examples, like ANLI and stuff like that. But I really haven't got great results on this more, we can say, more difficult task. So that natural language inference task, where we need to determine if two sequences are like entailment, neutral, or contradicting to each other. And yeah, it was a bit more tricky to make it work. So for instance, what I tried, I was training like a model on SNLI, and then I was evaluating it on NLI without training it actually on this adversarial natural language inference dataset. And the classification performance was really poor. The loss was kind of better, but the performance was poor. But here you can see, yeah, I'll check if I have the outputs. So yeah, let me just don't take too long. For example, here you can see that when we train with this, here it's called ALUM callback. So it implements the adversarial training for language. And you can see that validation loss does not increase as we train. Both accuracy and validation loss improve. But as you would usually see without this adversarial training, the accuracy keeps improving while validation loss grows. And that essentially means that the classifier is overfitting on some examples and is overconfident in some wrong predictions. But here it's not the case. Yeah.
I have another question.
Okay.
Do you apply this adversarial loss on every training step, or are you doing it once?
Yeah, it is applied on every training step. So yeah, we need to kind of smoothen the loss. So we need to apply it during the training. And we have some experiments with schedule, like, for example, we start without adversarial loss, then apply it, and then like decay the weight on adversarial loss. And that seemed to produce better classification accuracy. But if you decay the weight of adversarial loss, it will again ruin this adversarial robustness. So
yeah, actually,
there is still some kind of trade-off.
Yeah, and we'll see the loss landscape, or not loss landscape, the schedule for combining the losses, and you can do that under different schedule, exponential, linear, and things like that, and they kind of share some of the data, I believe, for images, but I could be wrong. We get into that a little bit later in this lecture as well. Thanks, Sato. That was helpful, because eventually, as with a lot of things, the theory is complex, but when you implement it, then it becomes fairly simple. And it's kind of good to know that all you need to do in per iteration is one iteration and you're done, or two at most.
Yeah, I often see it's the case when some computationally expensive stuff is applied in this cycle. It's often done like only once, and it works. I have encountered this pattern in a couple of other places as well, and it seems
we saw that
to work.
Yeah, we saw that in, I think it was self-supervised learning or GANs or whatever too. I forget now, but I think in GANs we saw one where the per iteration, and when it came right down to it, you just do it once and you're good to go. Okay, thanks. That was helpful or insightful in terms of application rather than just a theory. The thing to understand about the paper, remember, just to provide the context, there were 4 different techniques that this paper was comparing. So one is pi model, temporal ensembling, mean teacher, and then this virtual adversarial training. So the basic ResNet that they use for this technique is typically in a ResNet, you do this bottleneck, right? You which they use a 1-by-1 con to reduce the width of the network, and then kind of do the convolution, and then you stitch it back in. That's the residual path versus the direct path. In the case of this particular paper, they use a basic wide. So they drop there's no bottleneck, as you can see, compared to this. It's directly using multiple 3x3s and none of this 1-by-1 con to reduce the width. And then they apply the dropout. So this is the basic wide. And by the way, wide, and this is something that I often get confused with, but basically wide refers to the number of channels that you use. right? The depth is something that is with respect to the layers, and the width has to do with the number of channels. So they use wide ResNet, which means they use a lot of channels in the ResNet, and they don't use the bottleneck layer, and then they use the dropout layer in the wide. So it's wide with dropout. That's the basic backbone ResNet that they use. And then the data is shared, as I said, typically on CFAR 10 and SVHN. And you can see typically in CFAR 10, it's like, I believe, 50,000, 10,000, 50,000 labels data set. You use only 4,000. You can see in supervised training, if you did supervised training with 4,000 labels and for SVHN you use only 1,000 labels, then you get, even in a supervised technique, you get 20% error rate. These are error rates, so lower is better. So as compared to some of the comparison of the four techniques, this is actually a combination of two things we have seen. One is the virtual adversarial training, the details of which Artur shared, and combined with minimizing the entropy on the unlabeled data, the very first idea that we saw. And we see how low the error rate can get, and you can compare that to the supervised learning, how much more the error rate is at the low data regime. So this is something Merchant, for example, is just comparing at a single data point. They do not provide the reference of how good this is at the full the available label data regime, but low data regime, VAT plus entropy minimization, or just even VAT. VAT stands for virtual adversarial training. And you can see that the error rate is very low. It's the same thing for SVHN with just 1,000 labels. It's at 5.35. On the other hand, supervised is at 12.83. Right? So better. Now, the interesting thing is the paper was written well and did all the right things, in the sense that they even show that actually the baseline itself, because of the rigor with which they did it, they show that in previous papers, they did not do a good job of setting up the baselines correctly. So even these guys' baselines have improved in terms of error rate for the 5 models. Okay. So even though the baselines has improved, but it still is the case that VAT and other techniques give much lower results. Now, one interesting twist, and it's kind of related to something we touched on earlier, and although they, at least in this portion of the lecture, they don't explain it, but subsequently we'll get into details where we get into a little more of an explanation, which is what they observed is, obviously we saw this, that VAT with entropy minimization and with only 4,000 labels on CFAR 10, you get a lower rate of 13.13. But here is the interesting or tricky part, right? Which is, if you take a pre-training of the network you're using, and you pre-train on ImageNet and then use the network to predict on CFAR 10 using these techniques, it actually gives a lower error rate than 13.13, right? And this is interesting partly because this is interesting or relevant partly because this is not what we expect to happen, right? Because the ImageNet distribution of data is different somewhat from the CFAR 10. So this is not easily explainable why we should get better results on the error rate when pre-training on ImageNet. So they kind of said, oh, there are certain images or some things that there is overlap, so let's get rid of the overlap. Maybe that's the reason why we get it. And even with removal of overlap, they still get lower results than that. Now, the thing is, in the rest of the lecture, maybe they explain it in the paper, but there is no explanation for why this is the case. But we will see discussion around the fact that because the reason why this is counter to our intuition is because if you remember, we said that the basic assumption in semi-supervised is the marginal distribution that we are training on, which is the unlabeled data, is the same as that of the labeled data. But here, even if it is different, you're getting lower. That's not what you would expect. You would typically expect, if it is the same, to get a lower thing. So that's somewhat not explained, but he just highlights that that's something. Maybe it is explained in the paper, but at least in the class, it's not. And we'll kind of see how we sidestep this issue in the future of what if the unlabeled data distribution is different from the distribution that you have for the labeled data. Anyway, moving on, you kind of look at the extent of the labeled unlabeled class mismatch. Unfortunately, I think Gochan has dropped off, but you can kind of see that this is, it shows that as you vary the number of or the amount of unlabeled data, the performance of many of these techniques drops. All of these techniques drops, I should say, but by and large, VAT still continues to do the best. This is that yellow curve or the triangle here, right? So as you drop the amount of unlabeled data from 100% to close to 0%, that is, you don't have labels at all, VAT continues to be better than the others. This chart shows for CFAR 10 and SVHN, the two different things. For SVHN, as the number of labeled data points drops from say 8,000 to as low as 250, you are kind of still in a very, you can see that the VAT curve is pretty flat, which means that all the way from 8,000 data points to 250 data points, your VAT curve still gives you a very low, somewhere in the 7% or so test error. Now, unlike in CFAR 10, as you drop from 8,000 to 250, it climbs and is close to 50% error, but VAT continues to do better. There's not much of a difference to that lower regime. But if you are in the 1,000 kind of a regime, or even up to 2,000, which is 1/4 of that, you still are getting less. And here, obviously, maybe 12 or 15%. Right. So the paper, this particular paper, which compared all these techniques, it kind of came up with some lessons. Now, this is where I said that one of the things takeaway is not all of these lessons are relevant now, meaning some of them are no longer true. So the standardized architecture plus equal budget, this is just how they did it. These two things are no longer true from what is discussed in the class, meaning he says, oh, this paper was published quite a while back. So it's no longer the case that unlabeled data from a different classification is not that useful. So as I mentioned, we have come up with techniques to make the violation of the fundamental assumption, or one of the assumptions about semi-supervised learning, meaning the distribution of unlabeled data should be identical to the distribution of labeled data. We have come up with techniques to overcome that limitation and say, well, that's not required and you can still see better results. When the paper was published, that was not the case. Today, it's okay if the distribution of unlabeled data is not, and you have techniques to overcome that limitation. And then here he says that most methods don't work well in the very low label data regime. This is no longer true either as well with some of the modern techniques. And then here is the thing that we observed, which is, somehow if we do pre-trained training on ImageNet, it produces lower error rate. The question of why is unanswered. And then, of course, it was on CFAR 10 and SVHN. Now, the remaining portion, and hopefully we'll be able to get to all three. I might have to rush a little bit, but there are three modern techniques which they discuss: unsupervised data augmentation, mix match, which Yuri asked about, and noisy student. So we'll quickly go through each of these. So the unsupervised data augmentation, what it is. Now, as we've seen in supervised learning as well, data augmentation is a huge part of why we get the results that we see, right? And so the thing that unsupervised data augmentation or this paper did is how to apply this aggressive data augmentation in an unsupervised manner and for the consistency training. And consistency training is the label consistency technique that we already discussed. Now, interestingly, the rest of the slides here discuss the application of this technique in kind of a language model context, even though the first image is that of a image, or the first discussion or slide is regarding image. So, you take this image and you augment it in various different ways. and you use the auto augmentation to kind of apply aggressive augmentation of color, frequency, noise, blah, blah, blah. Interestingly, in the NLP domain, one of the ways that they apply augmentation is through this technique of back translation. So for back translation, it's essentially the concept is that you translate this sentence. Let's say if this is an English sentence, you translate it using a sequence to sequence or a transformer method or whatever, and go from, let's say, English to French. Okay. And then the back translation part comes in translating from French back to English. So that's why it's called back translation, because you go forward and then you go back and you get, let's say, variations of the same sentence. Why? Because obviously going through this process, there is some amount of entropy or noise in the encoder decoder going forward. There's some amount of noise. So you're not likely to get the exact same words as for the sentence that you have gone through and back translated. That is forward translation and then back translation. So if you see the first two sentences are pretty reasonable augmentations of the first sentence, although the third sentence is somewhat of a different meaning, but the first two sentences are somewhat related. And this is an interesting way to do augmentation in the NLP domain, right? So, so the idea of unsupervised data augmentation is the following, that let's say we have the label data of X and Y, right? Then we train a classifier, as we've seen, of P theta of Y given X using standard cross entropy laws. Now, in which we optimize the logits of the true class, right? Then we have the unlabeled data and we add, as Arto went through, we add and gave a good example, we add like this noise to regularize the model prediction. And we add the noise in the VAT direction, right, where the gradients are calculated. He showed how the gradients are calculated and we make that add the noise in those adversarial directions. And we then calculate the unsupervised consistency loss, right? And we take the noise version of the model and the original model and make sure that the logits of the same layer are roughly similar. So that's kind of the basic idea of unsupervised data augmentation, right? So what we do here is on the left, basically take label data, supervised cross entropy laws. We have the label, we train a model, which is in our traditional model, traditional method of training supervised classifier. In addition, in UDA, you take unlabeled data, you add noise in the VAT model that Arto showed us in the code, and we make an unsupervised consistency loss, and we combine the unsupervised and the supervised in order to create the final loss. And the manner in which these two things are combined, you can have different schedules for combining these, okay? And this part on the right is what kind of Arto illustrated in the code, the virtual adversarial training to make the model robust to noise in the adversarial direction using unlabeled data, because as he showed, there was no need for labels in the portion of the code that he illustrated, right? And here is a very fascinating illustration, pictorial, but it kind of is, I think, interesting illustration of how you know, the data, the label propagation happens. So in the top, you can see that there are only 8 data points. And as we go through and do the VAT training, the virtual adversarial training, it kind of begins to, from each of the points, you can see the data getting smudged or distributed across. And by the time you do 1,000 updates, you can see that much of the rest of the data is being, or this distribution, which is, I forget now, 2 moons or half moons or whatever. And this kind of a basic distribution, that underlying distribution, you have much better chance of capturing it using the VAT technique. But it's kind of in the UDA paper, they show an illustration of how VAT does a good job of even from just 8 labeled data points with a heck of a lot of unlabeled data points, which are all the grays, and only having 8 labeled data points, you're able to get a much better understanding of the underlying distribution, right? So the point of this UDA is it's also applicable in 2 different modalities, if you will. For example, in case of images as well, you can use a lot of auto augmentation to produce the type of augmentations that are needed in order to generate the adversarial noise and then train the label consistency through unsupervised methods. And the augmentation that you do and say that these 2 things should predict the same and have consistency between the predictions, even when you add the noise, the augmentations are done. If it is NLP, through back translation, through TF-IDF type of word replacement, and if it is images, you can do auto augmentation. So you can use a different set of techniques, but the basic underlying unsupervised data augmentation can be applied, therefore, for both NLP and well as for images. Right, and this is just an example of what I talked about. Back translation is used for text classification. You go from English to French to English. Oh, one other thing that they do is in the softmax, which is used to actually classify. If you've seen before, there is a use of temperature-based softmax, and by modulating the temperature used in the softmax, the temperature variable beta, you can have a much more diverse situation that is producing more diverse output with high temperature, or producing better quality but less diverse output through the temperature setting being low, right? And then you use auto augmentation if it is images. You use the back translation if you want to generate the augmentation for text classification or NLP. And they share the results for language. And obviously, BERT large gives you, and again, keep in mind that some of the reference numbers for these data sets are enormous, right? And then they do, these are just results that are shared I'm kind of going to push through the results since you can look at them at leisure. But the bottom line, what they show, since we have less time and I want to get to the other 2 techniques, what they show is, you get state-of-the-art result on IMDb, and the amazing thing is you get that result with UDA and with 20 samples as opposed to 25,000 samples. So in supervised training, it's 25,000. With semi-supervised UDA, with all this back translation type of augmentation and stuff, you are at really impressive 4.20. The thing I don't recall is, what these numbers actually represent. If anybody knows, please chime in. What is the metric that is shared here? The other thing that is, sorry?
The metric is error rate.
Error rate, okay. The one other thing that is interesting in UDA paper, the other concept they introduce is that of training signal annealing. Right, and that one is one where, interestingly, you prevent overtraining on the label data. So what that means is you introduce an identity function and you say that if my output is, if my classifier is fairly confident already on certain set of inputs, then I don't continue to train on those inputs. So what it means is you only train on examples, new examples, especially in the labeled data regime where your classifier is not highly confident. So that's kind of an interesting twist. So you mask out the labeled example based on the confidence scores, right? And what does this help do? It helps to prevent overfitting on, therefore overtraining on labeled data. So it's interesting because you can kind of think of it as setting a threshold. So if initially you would have the threshold be set to be low, if as you train, the threshold grows because your confidence grows, and as your confidence grows, if you have set this threshold to be at a particularly high value, then you say, if my confidence is already this high on this set of this example, then I'm not going to train. And if it is only below a certain confidence level, do I use that example in training? And this helps prevent. And I was like, okay, how do you prevent training? And again, as with most things, it turns out it's just simple. You just prevent back propagation for those examples, thereby preventing the adjustment of the parameters for those particular examples. So a very simple technique, but a kind of an interesting play on not training on additional or more highly confident examples. Right. And you can play with different schedules for this threshold. That is, how do you adjust the threshold? There's a linear schedule, which is this line, and then there's a log schedule, which is this guy, and then there's a exponential schedule. And they kind of experimentally determine that, different schedule works for images than for NLP. But here is the beautiful kind of final result, which is pretty impressive. They show that, and this is kind of achieving the dream, if you will, because in the high data regime, they achieve much better results than your supervised training gives you, which is kind of the BERT fine-tuned model, right? And this is the previous state of the art, and you can see that they've beaten that. And in the very low data regime, again, they get, and obviously you have to keep in mind this is a scaled stuff, 93 to 96, but they do go from 93.5 to about 90, a little bit lower than 96. So this graph kind of shows you, at least in NLP, that the dream effect has been achieved of semi-supervised, which is not only in the low data regime is the performance better, but the performance is better by several percent, at least a percentage or so, or somewhere in that order of the high data regime as well with UDA. In vision, again, they kind of go through and compare different methods. UDA gives you extremely low error rate of 5.27. These are some, besides the wide, these are some advanced techniques or methods, and they use Mongo number of parameters compared to the basic 1.5 parameters. And when you're done with adding that many parameters and stuff, you're down to 2.7 error rate on a CFAR10 with only 4,000 images. Pretty unbelievable that it's like less than 3% error rate with 4,000 images, when the label data is about 50,000 images that you have. And that's kind of what this thing talks about. And with more advanced architectures, you can see that UDA gives as good a result as with supervised data. And then they did some ablation to show that augmentation is kind of one of the major contributors. So you really need, and I think Arthur touched on it earlier, that you really need some very aggressive and varied types of augmentation in order to ensure that you are able to maintain the label consistency through all of the data augmentations. So the UDA, data augmentation is an effective perturbation. It significantly improves, and it's applicable for both language and vision, and then it also works with transfer learning. And then for UDA with unlabeled data, ImageNet, they kind of, supervised top-one accuracy with 10% label data is only 55.9, whereas with UDA you get much higher, and you can see the top-one accuracy as well. This is one where they applied the technique of UDA to not just the ImageNet, which is 1 million images and stuff, but also the case of JFP, which apparently is 3 million images, if I recall, or more, and that is something that is the very high data regime, if you will, and they'll show subsequently that UDA continues to perform state of the art and give us state of the art results. And then this is just a study of the different schedules that I talked about, of how to use the schedule in these two cases for NLP and stuff, and they show that the linear schedule works better for images and the exponential schedule for languages. And the one other thing that they do, which is in addition to entropy minimization, software temperature control, these two things we have already seen. This is just temperature variable in the softmax. This is entropy minimization. We have discussed that. They do one other thing, which, as I mentioned before, is something that is helpful in also making sure and overcoming our limitation of the data distribution should be, remember in the very beginning, I mentioned that one of the assumptions of semi-supervised learning is the data distribution for X, that is the data that we use for unlabeled, comes from the same distribution as when we do for the labeled classifier. But this technique of confidence-based masking helps us kind of overcome that limitation and no longer have it be applicable. So what it does is, in this basic intuition behind this technique is domain relevance data filtering. That is, essentially the concept is filter the in-domain unlabeled data from out-of-domain unlabeled data. So basically, if you have a lot of unlabeled data, but you don't know which of the data comes from or is assumed to lie in the same distribution as what you're using in labeled data, then you use this technique of confidence-based masking to exclude the data from your unlabeled data points that don't, by your assessment, fall into the same distribution. So by doing this, you have kind of overcome the limitation, or in other words, you have kind of chosen from the unlabeled data, the data that you would like to use because you believe that it is in the same distribution. So that's what the confidence-based masking approach does. Right. So in addition to entropy minimization, softmax temperature control, they also apply confidence-based masking, which helps them get these good results. Mix match, this is the one that Yuri kind of asked the question about. Here, the technique, as I understand it, is the following: that you take a lot of unlabeled data, you classify it, you take the average of the classifications for any of the unlabeled data, you kind of average it, and then using the temperature type of approach, you sharpen it, right? And use this to kind of push the data of unlabeled data. You kind of divide the data into what is in domain and what is out of domain. And in addition, you do this mix-up application to this semi-supervised training. So how do you apply mix-up to semi-supervised? So essentially, it's the same mix-up technique, but applied to the unlabeled data batches and to the labeled data batches. So you just combine two unlabeled data and in some proportion, and you make sure that you combine them label data as well in the same proportion. And you ensure that you apply the label consistency for both of these combinations. So if there are mix-up related papers, and if you're not familiar, I'd encourage you to go look at the basic idea of mix-up in case of just simple supervised training. And mix-match just extends the mix-up into the domain of semi-supervised training. So you apply mix-up individually to the labeled data batch and to the unlabeled data batch. So that's the mix-match walkthrough. Essentially, for each of the batches, you kind of, apply the data augmentation. Then this is important. You average the predictions across all the augmentation. That's, if you will, this part. The averaging is very important. Then you sharpen it using the temperature, and then you take the augmented labels and their images, the augmented unlabeled examples and the guessed labels, and you do the shuffle. You apply mix up to the label data and the entries, apply mix up to unlabeled data, and you do that repeatedly. And that's what is referred to as mix match. Right. And then you combine the losses. Obviously, the consistency loss is some distance metric, and otherwise there is the entropy loss for the label. And then you combine them, and you see that mix match. And these are the comparisons of various techniques, and you see that mix match does really well as you change the number of data points for the test error, for CFAR10 and SVHN. Right, so that's giving you some of the data points, and then we come to the last paper, which is that of noisy student, and this I believe is one, and I think Arto referred to it at the very beginning. It gives us the best results, state-of-the-art results, self-training with noisy students, especially in the ImageNet, so large images and so on. It has helped us get to this stream goal of getting better results. And here is the simple idea. You first do the training, you infer the pseudo labels on the unlabeled data. You do that on those images which are where there is high confidence of the classifier. And then you utilize this and you do a lot of data augmentation, stochastic dropout, depth of the network is changed. You apply dropout, you apply data augmentation, and you train the model with the VAT kind of noise injection. And here is the incremental change at this technique provided. You then, using this technique of inferring the pseudo labels, you train a student model. This is think of it as a teacher model. Then you train a student model doing all this, generate a bunch of labels. Then here is the additional trick. You make the student a new teacher. So you go through this, you have now got a new model. You make that model the teacher, and you go through it again. You go through the whole loop again. Don't know how many times, maybe Arto, you would recall, I don't know whether in the paper they kind of say how many iterations they go through in order to get to the results that they publish. At least they don't talk about it in the class. The basic experimental settings are discussed here. Input noise is rand augment, then they do the dropout and stochastic. The basic network, by the way, they use is efficient net, which is different from the rest nets that are being used in the previous paper. Pseudo labeling they do is soft pseudo labels. The data set is 1.3 million images. The unlabeled data set is 300 million unlabeled images. And when they go through the iteration, and maybe this answers my question, maybe they go through like 1, 2, 3 iterations. And then the iterative training, they start with a large efficient net model, go through variations of it, iterations of it in this iteration that I talked about, and come up with results that Arto referred to, about 2% improvement compared to the state of the art before in top 1 accuracy. So let's get to that, 86.4 versus 88.4. So a good 2% improvement in top 1 accuracy, 35% error reduction here, and an order of magnitude less data, because you can see that this is with 300 million unlabeled images. This is 3.5 billion Instagram images. Of course, the number of parameters is very significant. It's no longer even in the 26 million. It's like 480 million. But it's less compared to this guy, which uses 2x the number. So it was able to achieve with half the number of what was previously done with these wide networks using ResNet, but here using EfficientNet L2, a 2% increase in the. And what they also show is that in the not only is the B7 good, but you can see about a 1% improvement in every one of the efficient networks, B0, B5, B7, and stuff. Also, what they continue to show is ImageNet A, B, C are apparently, much like Otto was referring to in the natural language processing, these are, it seems, corrupted or disturbed, perturbed ImageNet models with noise added to them. So difficult images that cause significant drops in accuracy to state-of-the-art models, and they continue to perform significantly better and give state-of-the-art results under ImageNet A, ImageNet C and P, same thing, and lower number means mean corruption error and mean flip rate, and they continue to get with the noisy student the best results. Right, and this is a very interesting actual example of things. You can see that in case the left-hand side, what is shown are the actual results, the right are the wrong results. So black text are the correct predictions made by this noisy student, red text are incorrect prediction made by baseline. So in all of these cases, you can see that the basketball is picked up by the classifier, whereas there is some random parking meter observation that is given. And again, this is, I thought, very fascinating because this is an image of a rack and it correctly identifies it as a plate rack, whereas the other classifier baseline thinks of it as a refrigerator. And it's amazing because at a first look, even a human would think that this is a refrigerator shot, because it looks like this is the open door of a refrigerator, but this is a rack, like as you can see here, right? So fascinating how it's able to do so much better on these images. And same thing, it's able to catch the sea lions as opposed to the lighthouse. It's able to capture the dragonfly as opposed to seeing some kind of a bullfrog. Able to capture the parking meter as opposed to the vacuum. There's a bicycle connected to the parking meter here. It's able to capture the swing in such an image. So bottom line, the importance of noise, there's just ablation to show that the augmentation and the noise that's added is very important in order to get the performance that we seek besides the augmentation. And why does the student model outperform the teacher model? Because of the addition of one of the things is, you know, all the stuff that's done at the left here. This thing, we use data augmentation, we use depth, we use dropout, and we use VAT kind of noise injection. So it's all these reasons that the noisy student model is even better than just the master or the teacher, if you will. All that leads us to the final thing, that semi-supervised learning is good and is useful. The promise has been kind of attained, which is it's good not just in the low data regime, but also in the high data regime. And with noisy student, we have seen excellent results for the second scenario. That is not just in the low data, but also in the high data. So that's it, folks. And we'll cover the next part. Next week, we won't have, because of the Thanksgiving in the US, but week after, we'll continue with the second part of this lecture.
Yeah, thanks, Srinivas. That's a really interesting topic. I guess it has a lot of like practical applications, because you know, labeling is hard, and everything that allows you to get better results with less labels is valuable. So yeah, it's unfortunate that you have so like really little about semi-supervised learning.
Yeah, I think, in fact, I'm curious to know whether, are you aware of any further work in the year and a half or so since the class ended about beyond this noisy student type of approach as to whether people have achieved even further improvements?
Yeah, so this meta pseudo labels paper from the same team was also impactful, and it's also was approximately the same jump in ImageNet performance, I guess, as noisy student. And there, the idea
Oh,
is
what is the name of the paper? Could you post a link to it
yeah,
on
yeah,
Slack?
I will
That'd be great.
post a link. Yeah, also I saw there is a lot of different research. I saw some good results with something like Moco plus self-training, but I haven't really went into details how they implemented it. And yeah, that's. But
because there's even a Moco version 3, which apparently is the kind of state of the art from when I saw in the papers with code stuff. That and there's some other variant that is there. So yeah, I mean, this domain, as you say, is really where a lot of the effort has been in the last couple of years, at least, of pushing this much faster. So it's kind of fascinating. Okay. Thanks, Arto. Thanks, everybody, for joining, and I'll see you all in 2 weeks.
Yeah, thank you. See you.
Sure thing. Bye.